The prediction of the molecular geometry of the xenon hexoxide ion using the Vesper theory, valence shell electron pair repulsion theory. We draw the Lewis structure first. Xenon, the central atom, is found in the 8th group and 5th period of the periodic table. It is a noble gas and has already got 8 valence electrons around the nucleus. Xenon, though, has got d orbitals. Having d orbitals, it can form the expanded octet. The oxygen atom is found in the 6th group and 2nd period of the periodic table. It has got 6 valence electrons that can be used for covalent bond formation. The ion will accommodate 4 extra electrons. These electrons will be located on the more electronegative atom oxygen, so that we have got 4 oxygen atoms with 7 valence electrons and 2 oxygen atoms with 6 valence electrons. Central atom xenon, 8 valence electrons. 2 oxygen atoms having 6 valence electrons. 4 oxygen atoms having 7 valence electrons. We make use of a large bracket to indicate the charge on the molecule. As a first suggestion, we can suggest a dative covalent bond to form from the xenon to the oxygen with 6 electrons. The xenon atom will donate 2 electrons to an open orbital around the oxygen atom. Looking at the other bonds, we form the ordinary covalent bond where 1 electron is donated from the central atom and 1 electron is donated from a terminal atom. When the central atom has got d orbitals and we want to predict a molecular geometry that will compare better with the geometry measured in the laboratory, we change the dative covalent or coordinate covalent bond to a double bond, so that a better suggestion for a Lewis structure will be the central atom xenon bonded with a double bond to this oxygen, bonded with a double bond to the oxygen, and single bonds for the other 4 oxygen atoms. We've introduced 2 double bonds, but the correct structure of this molecule can be better described when we use resonance structures. The choice was to introduce the double bonds in these positions, but the double bonds can also be introduced either in these 2 positions or in this position here, that position there. So we make use of so-called resonance structures to describe the molecular geometry. Per choice now we make a double bond in this position here, double bond to this oxygen here, and then single bonds to the other 4 oxygen atoms. And we can continue writing resonance structures for this molecule. The average of all the resonance structures will represent the molecule. All the bonds will have the same nature. They will not have single bond or double bond character. The nature will be something in between. There is just one correct molecular geometry for the molecule. And when we look at possible distortions, we see that first, xenon hasn't got any lone pairs, but secondly, we haven't got either double or single bonds. We have got bonds that's exactly equivalent, and these bond angles then will not be distorted. We've got a central atom A bonded to 6 terminal atoms. For the molecular geometry, we first need to look at the electron pair geometry AB6. AB6 electron pair geometry will predict the octahedral geometry. The bond angles all equivalent, exactly 90 degrees. We predict for our molecular geometry an octahedral structure with no bond angle distortions, bond angles all 90 degrees. We make use of Cooper or Cowper structures to draw the molecular geometry. Central atom xenon, double bonded oxygens, single bonded oxygen atoms. Although we introduce the lone pairs on the terminal atoms, realizing that the lone pairs will not influence molecular geometry. Only lone pairs on the central atom will influence molecular geometry. We must indicate, though, that we can write several resonance structures for this molecule. And we can write even more resonance structures. The molecular geometry is then octahedral. Bond angles all equivalent, no distortions. Because we haven't got a double bond in this position, we have got something in between a double and a single bond. When we look at the molecule, we must realize that the molecular geometry will depend on the positions of the atomic nuclei in three-dimensional space. We've got the central atom xenon here, 6 terminal oxygen atoms. In this instance, we have got bonds, something of a single bond and something of a double bond character here. Not pure single, not pure double bond character, but they are all exactly the same. Bond angles will not be distorted, all the bond angles 90 degrees. The prediction of the molecular geometry of the chlorosyl tetrafluoride ion using the Vesper theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Chlorine is the central atom. Chlorine is found in the 7th group and 3rd period of the periodic table. It has got 7 valence electrons to form covalent bonds. Chlorine has got d orbitals. It can form the expanded octet. When chlorine is the central atom, it can form either single or double bonds. Oxygen is found in the 6th group and 2nd period of the periodic table. It has got 6 valence electrons for covalent bond formation. The fluorine atom is found in the 7th group and 2nd period of the periodic table. It has also got 7 valence electrons for covalent bond formation. The ion will accommodate an extra electron. The extra electron is accommodated on the more electronegative atom, the fluorine atom. Central atom chlorine, 7 valence electrons. Oxygen, 6 valence electrons. 3 of the fluorine atoms having 7 valence electrons. One fluorine atom has already got an electron octet. We can suggest then a dative covalent bond to form from the fluorine atom with the electron octet. That means that the fluorine atom will donate 2 electrons to an open orbital around the chlorine atom to form a single bond. Here we can form ordinary single bonds where one electron is donated by the chlorine central atom and one electron is donated by the fluorine terminal atom. We can suggest a dative covalent or coordinate covalent bond where the chlorine atom will donate 2 electrons to an open orbital around the oxygen atom. This will give an electron octet to the oxygen atom. Then we can pair these 2 electrons and then we've got a lone pair on this central atom. When the central atom has got d orbitals and we want to predict a molecular geometry that will compare better with the molecular geometry measured in the laboratory, we change the dative covalent or coordinate covalent bond to a double bond. We do not change the dative covalent bond of the fluorine atom to a double bond because the fluorine doesn't have any d orbitals. So the chlorine atom then, forming a double bond to the oxygen atom, and we have still got the electron octet around the oxygen atom. We have got 3 single bonds to fluorine atoms with 7 valence electrons. We have got a lone pair on the central atom, and we've got a dative covalent bond where one fluorine atom with 8 electrons will form a dative covalent bond to the central atom. For the prediction of the molecular geometry, we have got a central atom A bonded to 5 terminal atoms and 1 electron pair on the central atom. Electron pair geometry is A, B, 5 plus 1 will make 6, AB6, that will predict an octahedral geometry. For the octahedral geometry, we predict bond angles of 90 degrees. In the place of one of the atomic nuclei, we have got a lone pair when we predict our molecular geometry. And we predict a square pyramidal molecular geometry for our molecule. We also expect some distortions in the molecule. The volume of a lone pair is larger than the volume of double bonds, larger than the volume of single bonds, and we expect these bond angles to be a little bit distorted. We make use of Cooper or Cowper structures when we draw the molecular geometry. Central atom chlorine, lone pair, one fluorine atom with a dative covalent bond, the other fluorine atoms single bonds, double bonded oxygen. Brackets, indication of the charge on the ion. We predict then a molecular geometry of being square pyramidal. The electron pair geometry was predicted as being octahedral. The molecular geometry is square pyramidal, where we've got one lone pair on the central atom, 4 planar positions for 4 terminal atoms, and the double bonded oxygen. The prediction of the molecular geometry of the chlorine tetrafluoride ion using the Vesper theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Chlorine is the central atom. It is found in the 7th group and 3rd period of the periodic table and has got 7 valence electrons for covalent bond formation. Chlorine has got d orbitals and can form an expanded octet. The fluorine atoms are also found in the 7th group, but in the second period of the periodic table. It has got 7 valence electrons for covalent bond formation, but it hasn't got d orbitals and can only form single bonds, being a terminal atom. An extra electron is accommodated in the molecule. The extra electron will be accommodated on the atom that is more electronegative. Fluorine is more electronegative than chlorine. So we've got a chlorine atom, 7 valence electrons. We've got one fluorine atom having 8 electrons, and an electron octet. And then we've got 3 fluorine atoms with 7 valence electrons. Covalent bonds can form where one electron is donated from the central chlorine atom and one electron is donated from the terminal fluorine atom. And we form 3 such single covalent bonds. To form a covalent bond from the fluorine atom having already got an electron octet, we make use of a so-called dative covalent or coordinate covalent bond. 2 electrons will be donated from the terminal fluorine atom to an open orbital around the central chlorine atom to form a covalent single bond. And then we've got 2 lone pairs on the central atom. So that a Lewis structure can be written as central atom chlorine, 2 lone pairs, 3 single bonds, to the fluorine atoms with 7 valence electrons, and a single bond, but a dative covalent single bond, to the fluorine atom with the extra electron. Large brackets, charge on the molecule. The molecular geometry, A for the central atom will represent the central atom chlorine, bonded to 4 terminal atoms, 2 lone pairs. The molecular geometry AB4E2 is represented by the electron pair geometry AB, 4 plus 2 will make 6, AB6. Electron pair geometry AB6 will predict an octahedral molecular geometry. Bond angles the perfect 90 degrees. For the molecular geometry, we have got 2 lone pairs in the place of 2 atomic nuclei. And we have got a so-called square planar molecular geometry. We make use of the Cooper or Cowper structures to draw the molecular geometry. Central atom chlorine, fluorine atom with the dative covalent bond, ordinary single bonded fluorine, 4 terminal atoms. Two lone pairs on the central atom. Molecular geometry, square, planar, bond angles the perfect 90 degrees. The electron pair geometry predicted an octahedral geometry. For our molecule, though, we have only got 4 terminal atoms and 2 lone pairs on the central atom. Molecular geometry will depend on the positions of atomic nuclei in 3-dimensional space. Central atom atomic nucleus, fluorine, 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 fluorine atomic nuclei. And we've got a plane That's a square planar molecular geometry.